Okay, so here was our iterative version of a binary search. By the way, it's called a binary search because you split things in half. Okay, and most people, when they use a phone book to do a binary search, really try to optimize it a little bit and guess approximately where within the range the thing is going to be. So if you're looking for Zs, you don't necessarily split the phone book in half. It turns out that it really doesn't make all that much difference, because like we said, million entries in the phone book, it's going to take you no more than 20 questions, 21 questions to find out, to do the splitting. So if you save one or two either way, not really a big deal, even on very large numbers of things. So even just splitting it in half works about roughly the same as taking a good guess. Okay. How did we go about doing it? Well, we called find number to do all the work, and find number has two cursors that it's given, left position and right position, and the name of the game is just to take the middle and then say, figure out, well, either I need this side of the phone book or that side of the phone book, and throw away the other. And it's the throwing away of all of that information, half the information at a time, that makes the thing efficient. Okay, so the only good data is data that you don't have to process in performance terms. Okay. And then after that, it's a matter of, oh, well, let's just calculate the middle position. If we land on the correct one by accident, really, we're done. Otherwise, oh, I guess we have to adjust the cursors to only look at the side that we're interested in, and we'll just keep repeating that until we're done. Okay. Notice that in most textbooks, when you see it, they'll use really strange variable names for that sort of thing, which makes it very difficult to figure it out. So the variable names really make life a lot easier here. Okay, so let's do the same thing with recursion. So I've basically duplicated the code, I've duplicated the unit tests and changed the name. This is now the recursive version, same data. We've got find number here, all set to do whatever work we need to do. Okay, and I've said in terms of recursion, in terms of the pattern, this is the start of the fence painting. This is somebody coming along, the, you know, like Mum in the Tom Sawyer thing, and saying, you need to paint the entire fence. Okay, so it's, you start the recursion by usually having something at the higher level that says, here, go, operate on the entire thing to solve the problem, and then the recursive routine will do the splitting up of the problem afterwards. Okay, so recursion, best way to approach it is to start out and think of, in this case, what's the lucky thing that would happen if you are looking for something. So to just do the job of looking for one thing, what would you do if somebody gives you this full range? What was the first thing we did in iterative?
Find the middle.
So we'll find the middle and we'll see whether or not we land on the middle. So I'm going to save myself a bunch of typing by just stealing that code. So there's the eureka moment. I found exactly what I was looking for. I'm done. Okay. Now, next thing to do in recursion is figure out when you would stop. Sure, let's do that.
Well, either when you find what you're looking for or the enough list.
So let's do the, how would you know that you hadn't found it? I'm just going to stick a return -1 in here, whether or not it matters. So go and put in a case up at the top that says I would have nothing to do. What's the nothing to do case? If somebody was trying to fool you,
the left position is greater than the size, or the right position is less than 0. Yeah.
so almost the same thing as iterative. If the positions have crossed, then there would definitely be nothing to do. So we'll take the nothing to do thing and we'll slide nothing to do up to, oh, well, we definitely know in that case if there was nothing to do. Okay, so that's the stopping condition. Okay, and the only thing we're left with down here is, oh well, if we didn't find it, how do we hand out some other portion of work? Okay, now the portion of work could either be the left half or the right half. Okay, so we'll break this down again, actually the same thing we had for that almost, except I'm just going to leave out this portion for a second.
You can get rid of the else, can't you?
Yeah, we'll leave that for a moment. Okay, so if it was on the left-hand side, now here's the little recursive trick. When you want to do something recursive, I always think of it as being, well, I tried this one, it wasn't successful. How could I hand off some amount of work to somebody else? Now, technically speaking, it's not somebody else, but it's just always easier to think of it that way. So if the number was on the left side and I wanted to give it to somebody else,
Return find number.
I would say find number, same sort of stuff we'd said before, ordered numbers, number to find. And if it's on the left side, it's going to be starting from the left position. And this time, it's
Middle position on the top.
just the middle position minus 1.
But it should be return find number, not this one.
We'll get to that. Okay? So I'd ask them to do the work, only this time I would say, well, if it's on the left side, I only want you to do from the left side to the middle. It's someplace in there. And the other situation is, well, it was on the right side, so that's almost the same thing. Find number with number to find, this time from middle position plus 1 because we've already checked the middle to right position. Okay. Now, if you ask somebody to do the work here, go find me a number, the thing that they're going to give you back is either I didn't find it minus 1 or the position where they found it. So when they give you back the number, your reply to whoever asked you is
To return it as well.
what he said. Works for me. So that's whatever he says is good enough for me. Because I didn't find it, so it's up to him to go find it. Whatever he says, I trust him. So that's just, let's send the answer back. And so the same for this one, let's just send back whatever he says. And the compiler's smart enough to complain to say we'll never get to there, so we'll just leave that out. Okay, so if we look at this piece of code, just to double check, we've got the thing that starts the game going, which is here, start with the whole piece, or the whole amount of work to do. We've got something in here that does the work that I have to do for just the one tiny thing. Oh, let me check and see if I calculate the middle, if I landed right on there. And then we've got something that says, oh, we need to do a smaller amount of work given to somebody else with exactly the same set of instructions.
Shouldn't that while be an if though?
Yeah, that was just because I copied it from the other one. Won't matter. Okay, and the last thing that it's got is a reason to stop, which I always think of well, what if they're trying to fool me? What if they gave me nothing to do? What would I, how would I know that they were trying to fool me? Well, I would know if there was, in this case, they gave me two cursors that were backwards. Well, then obviously there's nothing to do. Okay? And that's more or less all there is to it. Why did I write this with an else? Well, you could leave it out and you could write it like this, which is exactly the same thing, and that's more in line with the way that we've been writing it. But to me, that hides the actual binary fact that it's either the left or the right. Okay, so this is the one true else case where I don't mind putting the else in here because it says almost exactly what it has to be. It's going to be either or, and that's all there is to it. It really is just one of those two choices, and the choices are really almost exactly the same, just depending on which side it is. Okay, every piece of recursion that you write follows exactly that same pattern. Right? The only thing that really sort of changes is, the thing that you have to do in here, however much work you decide to do. If you look at the ones we did with printing things out, it's almost exactly the same, printing forward or reverse. You do the work in the middle, you figure out how you don't have to do any work, and you figure out how you can get somebody else to do the work. Okay? And if we run that thing, I've got the same set of unit tests. The only thing I did was I changed it to recursive binary search, so it's the same ones we had before, and oops. Okay. So we'll go into the recursive one, and we'll go,
No, greater than.
Greater than or equal to?
Just greater than, yeah.
Okay, greater than, sure. Oh, because the condition changed because we do it in a different place. Okay, so run that version. Oops, ran something else. There you go. Okay, so I really just took the same sort of ideas that we had before for the iterative one and morphed them. And like I said, officially there's no difference between iteration and recursion. Some programming languages, like for instance Lisp, which goes back to the 1960s or 70s, whatever it was designed to be completely recursive. Okay? The thing I find is that seems to be only mathematicians that think recursively for those sorts of problems. So for the most part, it's in sort of the standard programming languages, it tends not to be used as much. Okay, questions about the simple one? Okay. The other interesting thing about recursion is that I find that the more complicated the problems get, the easier the recursion seems. Okay? Usually these sort of semi-mathematical ones tend to be less understandable than the bigger cases. So, let's go back and look at something we already did. And let's talk about our infamous let's hunt for beer in the forest problem. Okay, so here we were hunting for beer, and we had beer someplace. Okay, and we said the way we played this game is we had a to-do list, and we put the first place to check, and if we didn't find any beer there, then we mark that one, put the 1, 2, and 3 places onto the to-do list, etc. And then kept picking off things off the to-do list to do. That's essentially all that the algorithm was. Okay. Interesting thing about this problem is that this is a forest here, but that's also a forest, just a little smaller. That's also a forest, just a little smaller. And that's also a forest, just a little smaller. So rather than us doing the work of saying, I'm going to be the one that goes out and searches for beer through the forest, The other way to play the game is to say, oh, I'm going to check the 0 position in the forest, and then I'm going to call a friend and say, hey, would you mind checking the starting at the 1 position in this little forest here, and see whether or not you can find some beer for me. Okay? And if they don't find any beer, then you turn around and you call somebody else or the same friend and say, hey, could you go look in this little forest that starts here and see whether or not you could find some beer for me. Okay? So, interestingly enough, that problem is something that we might be able to handle with recursion. So what I've done is I've taken our forest code that we had that looked like that with the table of stuff, and we had this big long algorithm here to go search and do all sorts of things, and let's just see if we can rearrange this thing to do it the recursive way. And so what I'm going to do here is I'm going to wipe out a whole bunch of code, and we'll just sort of kind of start over here. So it's probably easier than trying to morph that code. Get rid of all that, and that, and maybe a brace or not. Okay, so let's think of this the recursive way, and change this to a recursive call that says hunt for beer in forest, and I want you to start at the 0 position in the forest. Okay, so there's the start of the recursion. We'll go here and we'll write public void hunt for beer in the forest. We could give it the forest, but I'm not going to bother at this point. It's just really the position in the forest I'm interested in.
If you're outside the main.
Yeah. Oops. Outside of something. Another brace. When in doubt. Oh, I don't want to do that. That'll destroy my clearing thing. What's it upset about now? Oh, static, sure. That'll sort of almost work. Yeah. Okay, so here's our recursive routine. What would be the lucky case?
Find it 0.
So if all clearings subposition dot get has beer is true, we'd say we found the beer at, I guess we can just say position here, can't we? Okay, there's the happy case, and we'll stick in a return there just so that we're done. Okay, there's the happy case. Okay, what would you do if you didn't find the beer in this case?
I'll hunt for beer for all child goods.
Go through the 1, 2, and 3, so go through all of the places we can get to and call a friend to go find the beer. So let's go through all of the places we can get to, clearing, a clearing, in all clearings, or sorry, in, I wonder if I can do that, all clearings sub position. See if I got my for each working, almost. Not quite. Well, that's fine. Let's just go look at the clearing class for a second. Clearing. It would be nice if I had an iterator, wasn't it? Wouldn't it?
Trying to get the connection.
Or get connections. We'll do get connections in all clearings dot. See if that
It
works.
should be int clearing. Clearing.
Let's just see here for a second whether or not that will make it happy.
Or int, like clearing position.
I don't think it's an int. No, there we go. So that gives just the numbers, right? Because clearing had an array of numbered connections. Okay. So we'll convert that into all clearings sub a clearing is that particular clearing number. And what do you want to do with that clearing number? Check for beer, and that's call somebody else to do the work. So hunt for beer in forest.
Let me just pass it all clearing, not all clearing stuff.
I guess we just pass it a clearing, don't we? As just the integer. That's fine. There we go. Hunt for beer in the forest, starting at that position. Okay. Now the only other thing we have to work at is
Nobody finds it.
so this thing, instead of being a void, should be an integer, so that we can say hunt for beer in forest and then system out print line. I guess we don't even need that. Print someplace else.
Printed internally.
Yeah, it's printed there, but I'll do it again here. Just, we can figure out which one we want later. Do it in both places. Just to make the compiler happy. So this would be a return position. If we didn't find it, it would be return -1. And what do you do here? Only one of those people is going to find the beer. So we'll get the position, we'll get the found position back from them to hunt for the beer. And if found position is greater than or equal to 0, meaning I found it someplace, return found position. Otherwise, just for fun, if I've done all of the clearings, actually, well, we'll worry about the print statement later. Is that it? Let's just double check. We start out and we say hunt for beer and forest starting at position 0. That's the thing that gets things going. The good case is oh, I discovered the beer, that's the only work I have to do is to just check this clearing, right? Do the simplest thing that I can do, and if I found it, we're done. And the case of getting others to do the work is we'll go through anything that I could get to from here, and we'll just ask somebody else to check that clearing for me, so I don't have to do the work. And if they happen to find it when they're checking, then the work is done. If not, we'll just keep going, and eventually we'll say that we didn't find it. Well, gosh, let's just run it and see what happens. It repeated it twice because we're printing it twice. Just just to make it more obvious, let's go in here and let's print out checking at a clearing to see whether or not we found it. Okay, so that says we're checking at that clearing. Just out of interest's sake, where would we print the going back to?
After the recursion call.
So somebody would check something like clearing 2, and if they didn't find it, they would come back and say, I hadn't found it, so you would be going back to clearing 0. So I'm going to change this one to going back to I think inside.
Still in the formula.
Going back to position. Probably bad name,
Oh, okay. I thought you were doing it now.
but there we go. And we'll save that and give that a try. And it's probably pretty close. I can't remember what our forest looked like, but it checked 1, checked 4, going back to 1. Didn't do the 0, but oh well, close enough. Okay, and eventually it does find the beer at 11. Okay, so not quite perfect, but close enough to show you there's the entire piece of code. Okay, so this is one of those cases where the recursive solution actually makes more sense to people, even though it's more complicated than some of the recursion we've been doing before. The recursion we've been doing before was just binary recursion. This has got a whole bunch of things going on, but it's still really easy. Well, I check mine, and if it's not mine, then I'll get each of the other people to go and check whatever they want to check for their portion of the stuff that they've got to do. Questions about that one? Which one do you think is easier to write? This one. Usually what happens, like I say, is you struggle with the other version first, going, why does this have to be so difficult? And then eventually you come along and you go, well, maybe there's a different way of doing this sort of problem. And if you try the recursive version, it ends up being sort of magic and going, oh, well, this is really simple. Why didn't I think of this before? Okay. Well, in the iterative version, we had a stack. We had a to-do list that was operating as the stack. Where did the stack go?
It's internal because it has to do with the recursive stack that we have.
Yeah, we're making use of the Java stack, which keeps track of how to get back to the previous method that was called, and the methods are holding on to all of the work, and so the stack disappears. It's still there, the information is still hidden, because this is really stacking up the number that's going to be used onto the internal stack. Okay, so they're all still there, they don't go away. You'll still see exactly the same thing in a stack trace where it goes down each one of the levels. It's just that the levels are all being handled by the compiler rather than by the stack. Okay? So quite often you need that stack to do the recursion. In this case, it's just buried in the problem itself, in the Java itself, and you don't have to see it. So it's a beautiful little solution to a problem. Okay, and we needed that so that we can take one more step in the process here. So I said I had to branch out and do recursion just because we were going to use it for something else, really. So let's go back and look at the simple recursion that we had. I'm just going to borrow some numbers here for a second. Those are the numbers that we had. We had 55, minus 55, minus 10,
23,
23, 57,
91,
91,
101,
101,
132, what is that, 130?
333, and 444. Okay. Let me take these numbers and rewrite them a slightly different way. I guess what doesn't matter. All right, oops. That looks like that. Not the best, but that's okay. I almost got it right. All that I did was I took what was essentially numbers on a number line. The rule for a number line, going back to, what's that, must be grade 1, was that that number there on the number line, any smaller numbers are to the left and any larger numbers are to the right. And I took that rule and I applied it here, and I said I'm going to put this number in here, and then any smaller numbers are to the left and any larger numbers are to the right. Okay? And the same for this one. You pick any number on the number line. 23, any smaller numbers are to the left, any larger are to the right. Minus 55, smaller is to the left, larger to the right. So the same rule still applies for each one of those things. Okay? So suppose I ask, gee, I wonder if the number 132 is anywhere in this hierarchy. How do I find 132?
Start at 101.
Start at 101 and ask the question, gee, I wonder if 132 is less than or greater than.
It's greater than.
It's greater than. Oh, I wonder if that's 132. Nope. Well, where would I check? Left or right? Oh, let me go left because it's less than. Oh, look, there's the 132. Notice that this thing plays exactly the same game as what we were doing recursively in or through our binary search. In either version, all that I've done is I've done it in a hierarchy instead of splitting things in an array. Okay? Exactly the same game. Well, let's try some other things with this. Suppose that I was looking for the number 35.
Start at 101.
35 has got to be less than 101. It's got to be greater than 23. It's got to be less than 57. There's nothing there. Oh, I guess there's no 35 in here. If I wanted to put the 35 in, where would I put it?
Right there.
Interesting property. If you don't find it, the place that you would put it is exactly the place where you didn't find it. which is sort of handy in itself. Okay? Let's play another game with this thing. There's a bunch of numbers. Let's build that hierarchy from scratch. We'll start with the first number, the 101. We'll plug it into our tree. Do the 87. 87 has to go less than the 101, so we'll plug that in there. 91 has to go less than 101, greater than 87. 91 goes there. 26 is less than 26. 53 is less than, stuck here for a second, less than, greater than. 53, 81 is less than, greater than. 206 is greater than. 119 is greater than, less than. So you can take any set of numbers that you want and you can plug it into this thing. And once you've plugged it into this thing, now when you're searching for numbers, it's really efficient because you're throwing away more or less half of the tree every time you drop down a level and say, well, it wasn't there, I guess I have to go left or right. How efficient is it to put those numbers in? Just out of interest, say.
Order in.
If, or put it this way, if my tree had 1,000,000 numbers, what's the maximum level, or what's the expected level of the tree? What depth do you expect to see in the tree?
Half.
All things true to me.
It's the same answer that I gave to how many splittings of 1,000,000 in a phone book would I have to do?
19.
20-ish for 1,000,000 items, whatever it happens to.
19.9.
Yeah, okay. So worst case for 1,000,000 items, if you completely filled each one of these things, they would fit into nothing more than a depth of about 19 or 20 items deep. And so the maximum number of times you would ask the question, where does this go, where does this go, or how do I find it, same problem, would be about the maximum depth, or about the depth of the tree, which is about 20. So the answer is log to the base 2 of however many items you've got in the tree, roughly, assuming that it's in reasonable order. Okay? So hold it here. If we had that ordered list of items in an array, and you wanted to find out where to put something, you could do a binary search to put it there, but then you would have to shuffle everybody down in order to make room for it. If you use this sort of node-based structure and you find the place to put it, you can just basically stick it into the tree someplace and be done with it. Okay? So it's very efficient to put things in. It's very efficient to search for things because it's the same as putting them in. Okay? What's worst case for this thing? For the shape of this thing? If I were putting numbers in, I randomly chose numbers here. Suppose that I'd chosen the numbers 1, 2, 3, 4, 5, 6, and started making a tree with there. Well, I put the 1 into the tree. Oh, I put the 2 into the tree, it goes on that side. I put the 3 into the tree, it goes on that side. I put the 4 into the tree, it goes on that side. All of a sudden, I've got a chain of things, essentially. And now I've gone from really good to really, really bad because I'm not making use of half of the tree ever. Okay, so it's really interesting here that if you take random things and lots and lots and lots of them and stuff them into this thing, what you're going to end up with is more or less a triangular shape. If you use things that have got lots of order to them, then you end up with a bad shape. So this works really, really well for things that are random, really, really badly for things that have got any order to them at all, which is sort of interesting. It works best for worst case and worst for best case. Yeah, okay. Okay. So for now, what we'll do is we'll just assume that when we're playing this game that we're dealing with all sorts of, a whole bunch of random things, and essentially we'll get a nice shape to the tree. This always reminds me of Charlie Brown's Christmas, right? This is like a Christmas tree. You get the scraggly ones with lots of stuff that you have to cut off the end and all of that, and they're poorly shapen trees. Those don't work very well for Christmas trees. So the same thing here. The more of a pyramid shape that you can get with this and keep things all scrunched up where they belong, the better off you are.
If you just did the number line trick with your ordered group of numbers, that would improve the efficiency.
Well, this is getting a little ahead of the game, but while we're here, notice this thing here that's hanging outside? How could I make this better? Do I have to reorganize the whole tree?
New starting number?
Move the 53 to where the 26 is, and then the 26 goes to the left, and the 81 goes to the right.
87, it would just shift.
Well, the problem here is the 81, right? More or less, it's like sort of 2 levels deep, and it would be nice if it fit someplace in there. Okay? If I took the 53 here, and I sort of brought it up, and I brought the 26 down, I would be essentially sort of turning it this way to drive that 26 down and the 53 back up into it. So if I took this thing and more or less rotated it left, I would drive it up this way. Okay? And if I drove it up this way, I would end up with the 53 here, the 26 there, the 81 there, and that would disappear. Okay? So it actually turns out that there is an algorithm for going and looking when you place something. If it drops down below the level where you want it, there's a bunch of conditions on how you can go and fix the thing in order to get it back up to where it's supposed to be. Okay? So it's possible to do. And by the way, I'm sure there's a guy who got his computer science doctorate in figuring out how to do that way back when. Okay? So in the 60s, that was an interesting thing. Now it's just sort of boring. Okay. Let's see. Let's try one more thing, just so that we wind up our tree activities before we write any code. There's my tree of things. Let me give you a small tree here for a second. A very small tree that looks like that. Okay? If I wanted, in this smallest case, to say those numbers, to get them out in order, which number should I say first?
5.
The 5, then
And
the 10, and then, so this is left, middle, right. Okay? You said the 5 first because you recognize that the less thans are on the lower side, or on the left-hand side of here. So we need to say all the ones on the left before we can say this one, and then we'll say all the ones that are greater than. Okay? So recursively speaking, it's do anything on the left, I'll do my work of saying the 10, and then get somebody else to do everything to the right. Okay? Let's apply that process to this thing. Okay, there's the 101. Rule is I have to say anything to the left first. So I'm going to hand off that thing to somebody else and say, there's a tree, I want you to go say it. He's going to say, oh, well, I can't say my node until I've found somebody to say stuff on the left side first. Okay, I'll get somebody to say something on the left side first. He's going to say, I can't say anything until I've said stuff on the left side first. Oh, there's nothing there. I guess I can say the 26. Okay. Then he says, anything to the right? Nope, I'm done. I'll go back to whoever talked to me. They say, oh, well, I've done all the smaller ones. I guess I can say my 33. And now the rule is I might as well get somebody else to do anything on the right, which is the 81. He says nothing left or right. I'll say that. So he says, I'm done. This guy says, I'm done. He goes back up to here. He says, well, since I did everything on the left, I'll say my node, and then I'll say everything to the right of me. Goes back up to him. He says, I'll say the 101, and I've done everything. Now I just need to do the stuff to the right. 206 can't speak yet because he hasn't done the left, so he'll do the left, and then he'll come back up to here, and 206. Oh, look, there they are in order. By the way, this thing is known as a tree sort. If you want things in sorted order, you take them into this type of tree, you dump all of your random things in, and then you go through calling them out recursively or whatever you happen to choose in that order, and they magically come out in sorted order. Okay? Which is kind of fascinating. Okay? And it turns out to be very, very, very efficient because plugging things in is log 2 to the base n, like the depth of the tree to stick them in. You get them all stuck in, so it's n times log 2 to the base n items, more or less. And then after you've got them all plugged in, you go through once and call them all out again, and off you go. Okay? But suppose you save those numbers to a file. Now what problem do you have when you go plug them back into the tree? They're in order, so you're going to get bad performance again. Just out of interest's sake, suppose that instead of doing left, middle, right, suppose I do, let's see, what's the other one? Middle, left, right. Let's give that a try. So if I do middle, left, right, I get 101 comes first. I did the middle, I need to do the left, so that's the 87. Did the middle, I need to do the left, that's the 33. Did the middle, need to do the left, that's the 26. Did the middle, need to do the right. Did the middle, now I need to do the right. Did the middle, now I need to do the right, which is that one, 206. Did the middle, now I need to do the, I think I got them right. I have to give this another try. There's a different set of numbers. All that I did was I went through in a different order. Let's take this thing and let's plug it back into a tree. 101 comes first, then I get the 87, which goes to the left, then I get the 33, then I get the 26 to the left, 26, then I get the whatever it was.
81. Actually, it's an 87.
That's an 87, so this is an 81, right? See what's happening? So this one is useful. Going through in that order is useful if you want sorted order. Going through in this order to take them out is useful if you want to take them out and rebuild the same tree that you started with. You just send them out in that order, plug them back in again, and you get exactly the same shape that you had before. Okay? The only thing that's left is left, right, middle. If you do the left and then the right and then the middle, you end up doing 5, 15, 10. Any use for that one? You always say the uppermost thing after you've said anything below it. You've actually probably seen these
Wouldn't that
things.
make like it into a perfect tree if you made it again?
No, it's useful. You know, when you click on a disk drive and you want to see all of the space that you've got on your drive and which folders are holding the largest amount of stuff, and you get the summary, right? You know, ever done that with those utilities that do that for you? So what they'll do is they'll calculate all of the folders below this one, and they'll tell you what the individual totals are, and then they'll say, oh, by the way, and the grand total for this one and all the ones below it is that. Oh, the grand total for this one and all the ones below it is that. So if you're looking at trying to delete stuff, you can go, okay, well, there's a folder there that has a lot of stuff below it for whatever reason, and you can delete the basics, the biggest stuff. Okay, so this other one is used for that sort of, I want a grand total working its way back up and still be able to see the individual pieces. Okay, so what we'll do on starting tomorrow is we'll turn this into Java code.